Hi, welcome to this tutorial on using the cumulative binomial probability tables. Now, I previously did a tutorial on this, and if you missed that particular tutorial, then what I would suggest is just go back to my website, look under tutorials for the binomial distribution, and you'll see how to use the tables for this. Just as a reminder, these tables allow you to work out probabilities when x follows a binomial distribution with n trials and probability of p of success. And they give you the tabulated values for the probability of x being less than a particular observed value x. So why would I want to do a second tutorial? Well, in the first tutorial I showed you, as I say, how to use the tables to do this. But sometimes you could be unlucky enough to have a set of tables where the p-value only goes up to 0.50. What happens if you've got probability values for p that are greater than 0.50? Does that mean that we can't use these tables? Well, the thing is, we can use them, and that is the aim of this tutorial, to show you how we can calculate probabilities when the p-value is greater than 0.5. So let me show you how. Now here I have an extract from the tables where we've got p going from 0.05 and 0.10, and we have n equals 5 and x equals 0, 1, 2, 3 and 4. So if we had a binomial distribution for x, it was distributed binomially with, say, 5 trials then, but the probability of success was 0.90 or 0.9, then how could I use these tables to work out other probabilities? Well, what you do is let y be a random variable that is distributed binomially with 5 trials, but only this time, since x represents the number of successes, y is going to be the number of failures, and the probability of getting a failure will always be 0.1. And what I would suggest, the best way of understanding how these probabilities work in the examples I'm going to do, just draw up a table. With practice you won't need to draw up a table though, you'll see how they connect. But for the moment, let's just draw up a table. Now x is the number of successes, and because we've got 5 trials, it can be 0, 1, 2, 3, 4 or 5. Now suppose we had no successes, then there must have been 5 failures, and since y represents the number of failures, this would be equivalent to y being equal to 5. Similarly, if x was 1 success, there must have been 4 failures. So y would have been 4. And so on. For 2 successes, y would have been 3, and then we would have 2, 1 and 0. Now if we were asked to work out, for instance, the probability of x being less than or equal to 3, we would be looking at these particular values, 0, 1, 2 and 3. And what would the equivalent y values have been? They would have been these values here, 2, 3, 4 and 5. So that would mean that the probability of x being less than or equal to 3 or less successes would have meant that we would have had the number of failures, which is y, being more than or equal to 2. Now, I can't use these tables yet because these tables only give the probability of being less than or equal to an observed value. But as I discussed in the earlier tutorial on using the tables, the probability of y being greater than or equal to 2, what we do is we know that all the probabilities would total 1, and all I need to do is subtract the probability that y is less than or equal to 1. I just need to work out these probabilities, subtract them from 1, and I've got these ones here. Okay? And now I can use the tables, because the probability that y is less than or equal to 1 is given along this row. We just look under p being 0.1 and we look along the row for 1, n equaling, or x equaling I should say, 1, and we got this value here, 0.9185. So put that in then as 0.9185. Do that subtraction, what do we get? 0.0815. Alright? So let's try another one. Suppose we're asked to work out the probability that x was, say, greater than a value, say 1. What would this be the same as? Well, if we want to have x being greater than 1, we'd be interested in these values, 2, 3, 4 and 5. So what would the equivalent y values be? They'll be these ones down here. They would be the values of y being less than or equal to 3. So we can say that this is the same as the probability of y being less than or equal to 3. And that's dead easy now because we've got this value in the tables here. Just look under 3 and we see we've got this value here, 0.9995. So we just got 0.9995. That was dead easy. Okay, we'll look at another one. Right, this time what we'll do is we'll look at working out the probability of x equaling a particular value. Let's say x equals 3. So if we're looking for x equaling 3, that's that value there, that corresponds to y equaling 2. 3 successes, same as 2 failures. So we can put that in then as the probability that y equals 2. Now the tables we know only give probabilities of less than or equal to a value. So to get round this problem, we just say that's the same as the probability of y being less than or equal to 2 minus the probability of y being less than or equal to 1. Because if we add up all the probabilities less than 2, 2, 1 and 0, take away these two values, 1 and 0, we're just left with the probability that y equals 2. So all we need to do now is just use the tables. So for the probability of y being less than or equal to 2, that would be that value there, 0.9914, minus the probability of y is less than or equal to 1, that's that value in there. So that's going to be 0.9185. Do that subtraction, what do we get? 0.0729. There you go. So that brings us to the end of this tutorial. I've been able to demonstrate a few ways of working out different kinds of probabilities here. So what I would suggest then is drawing up a table something like this, and then you've got your x values, got your y values, so whatever x values you need, just relate them to the equivalent y values, and then you should be able to use the table from there on. Alright?